Okay, so this is still section 10.5, picking up with problem number 19. We need to solve for x. We're assuming that BC is tangent to the circle, which means that this will be a right angle ABC. We can use Pythagorean theorem to solve for x. So a squared plus b squared is equal to c squared, where c is equal to x plus 6. So a squared plus b squared is equal to c squared. 12 squared is 144. Now we need to expand this. X plus 6 squared is not x squared plus 6 squared, it's x plus 6 times x plus 6, which we would FOIL or distribute. So we take first, outer, inner, last. First times first would give us x squared. Outside times outside is 6x. Inside times inside is also 6x. And our last term times our last term is 36. So let's simplify this. We can get rid of x squared on both sides. We can add 6x and 6x, and that's 12x. And we can subtract 36 from both sides. So we get 12x is equal to 108, and divide by 12, and you get 9. Number 21. Two segments that are tangent to the circle from the same exterior point will be congruent. So this tangent segment is congruent to this tangent segment. So 5x minus 9 is equal to x plus 7. Subtract x from both sides. Add 9 to both sides. And divide both sides by 4. Number 23, in the arbor shown, AC and BC are tangents to circle D. The radius of the circle is 26 inches. So I'm going to go ahead and mark that in here. From A to D is 26 inches. And EC is 20 inches. And we want to find each measure to the nearest hundred. So first we want to find AC. So let's take a look at the right triangle that we have here. If it's tangent, then that's a right angle. And if this length here is 26, then this length here also has to be 26 because they're both the radius. So that makes it pretty clear. To solve for AC, we'll call that x. Use Pythagorean theorem, where our hypotenuse is together 46. We get 676 when we square that, and 2,116 there. Subtract 676 from both sides. And take the square root. So AC is approximately 37.95 inches. So that's my answer to part A. To part B, we want to find BC. Well, that should be easy, since from the same exterior point we have two tangent segments. So two tangent segments from the same exterior point will be congruent. So if this side is 37.95, then this side is approximately 37.95. Find the value of x, then find the perimeter. So this entire length is 13. So from this exterior point, this tangent segment and this tangent segment are congruent. So if that's x, then I'm going to call this x. This tangent segment and this tangent segment from the same exterior point will be congruent. So if that's 5, then this is 5. Now I can solve for x. If this is 13 all the way across, let's just take 13 minus 5, and that gives me x. So from this exterior point, I have 7 on this side, and I would have 7 on that side. And from this exterior point, 6 and 6. So we have the first part. To find the perimeter, well, I would have two 5s, 5 plus 5, two 6s, plus 6 plus 6, two 7s, and two 8s. Simplify each of these, so 10, 12, 14, and 16, and combine all those, and we get 52 centimeters. And that's your perimeter. Number 27, find x to the nearest hundredth. Assume that segments that appear to be tangent are tangent. So, looks like our radius is 4. So that length here is also 4. So the radius from here to here is 4. And we want to solve for x. So basically we're looking at a triangle like so, where QT is 4, at T is a right angle because it's tangent, TS is x, and QS would be 4 plus 5. 4 plus 5 or 9. Use Pythagorean theorem. Here are my legs, A and B. There's my hypotenuse across from the right angle, C. So x squared plus 4 squared is equal to 9 squared. X squared and 16 is 81. Subtract 16 and you get 65. And take the square root, and x is approximately 8.06. Alright, here's a 2-column proof. Given that quadrilateral ABCD is circumscribed about circle P. So circumscribed, what does that mean? It means that the quadrilateral goes around the circle, and the circle will be tangent to each side, so at 4 points. So if that's the case, then we should be able to prove that AB plus CD, so the length of these two sides, is equal to the sum of these two sides. AD and BC. Oops, I had the wrong thing on the first part there. So this side and this side, there we go, will be equal to this side plus that side. Okay, that's better. So let's state our given information. Quadrilateral ABCD is circumscribed about circle P. Now, once again, what does that mean? So by the definition of circumscribed, what can we say? We can say that AB is tangent at point H, BC is tangent at point G, CD is tangent at F, and AD is tangent at E. With that said, what can we say when we have that those are tangent? So two segments tangent to a circle from the same exterior point are congruent. So I know that these two are from the same exterior point and they're tangent. So I know that AE and AH are going to be congruent. I know that HB and BG are congruent. Okay, two tangents from the same exterior point. So that length and that length are the same. GC and CF, FD and DE. So we have some congruent segments here. Let's see if we can somehow do some substitution. So let's take other things that we know and say what it's equal to. So above we were talking about AB, BC, CD, and DA. So by the segment addition postulate, let's say what each of those is equal to in our diagram. So AB we can get by adding AH and HB. BC we can get by adding BG and GC. CD we can get by adding CF and FD. And the length of DA, so from here to here, is the same as adding these two lengths, DE and EA. So that's segment addition postulate. So we can do some substitution based off of things that we know now. So we're going to take AB plus CD, we're going to add these two together, and that's the same as adding these two sides together. So if I say AB plus CD, that's the same as saying AH plus HB plus CF plus FD. Let's continue to substitute. Oh, also, DA and BC would add up to these two sides added together. And we'll continue to substitute. So AB plus CD, I want to somehow get this expression equal to this expression. Remember, that's what we're trying to prove. So can I substitute things here? I'll have to pick up here on the next video. So we'll pick up at step 5.